Every single day, major healthcare institutions all around the world generate millions of tons of disposable medical waste. But the way hospitals process this material creates a dangerous problem. Because manual segregation is difficult and risky for human workers, totally benign plastic items are routinely thrown into the exact same bins as highly toxic chemicals and infectious pathogens. This leads to an astonishing error rate. Up to 95% of what gets classified as hazardous medical waste is actually overclassified. Facilities are treating harmless plastics as if they were lethal. When that much excess volume overwhelms the system, the operational costs of running high-temperature incinerators skyrocket. Worse, it creates massive blind spots. Dangerous items like used sharps are mishandled in the chaos, increasing the risk of illegal reuse and the spread of bloodborne diseases. Engineers have tried building automated sorting systems to fix this, but those algorithms consistently fail. They fail because the underlying data taxonomy, the actual categories we use to define the waste, is systemically flawed. To solve this, a 2022 research team led by Ramani Varadarajan proposed completely replacing current guidelines with a strict, computable 8-class taxonomy. This table details the newly proposed classification system. The taxonomy assigns specific color codes to distinct threats, separating red microbiological waste from yellow pathological waste. This granular taxonomy is too complex for manual enforcement, requiring an automated machine vision system to sort physical items. The researchers designed a prototype pipeline named Autumn to do exactly this. It takes raw camera sensor data and feeds it into a feed-forward neural network to output a precise classification. But processing high-resolution two-dimensional images requires massive computing power. To make this classification lightweight enough for physical deployment, the team first had to solve a serious dimensional bottleneck. When a camera looks at a piece of medical waste on a conveyor belt, it sees an array of pixels filled with chaotic lighting variations, shadows, and background noise. A lightweight network cannot process that raw spatial data efficiently. The first pre-processing step converts the input to grayscale. Otsu's method then calculates an optimal binary threshold, creating a black and white silhouette. Next, a hole-filling operation turns the trapped empty spaces into a solid binary mass. Residual noise still persists. Graduation marks on the plastic create jagged, irregular edges. To fix this, a morphological opening operation dilates the boundary, smoothing the jagged marks, and then erodes the image back to its original size. What remains is a mathematically clean, noise-free shape. The pixel data is prepared for dimensionality reduction. Traditional computer vision often uses two-dimensional bounding boxes to identify objects. If a scalpel rotates on a physical sorting belt, the pixels inside the bounding box change completely, confusing the network. Researchers bypassed this problem entirely. Instead of analyzing two-dimensional shapes, they extracted a one-dimensional centroidal profile. This diagram shows the extraction math. First, the algorithm traces the outer boundary of the smoothed blob and calculates its exact geometric center, or centroid. A raycasting operation calculates the precise distance from the center point to every pixel on the perimeter. It essentially unwraps the outline of the object and plots those distances sequentially. This successfully reduces the complex 2D shape into a simple one-dimensional array containing exactly 150 elements. Here we can see the resulting profiles. A circular Petri dish produces a completely flat line because the distance to the edge never changes. Meanwhile, the long, narrow body of a disposable pipette creates sharp frequency peaks. This one-dimensional transformation achieves rotational invariance. If the physical object sins on the conveyor belt, the values in the array simply shift their sequence, but the profile signature remains identical. With the format finalized, the team faced a strict constraint: only 141 physical images. This matrix details their data augmentation strategy. To overcome the scarcity, they injected random numerical noise, values between positive and negative 0.5, into the centroidal arrays to create variations of each item. Generating 25 virtual samples per photograph scaled the training data up to over 3,000 inputs. They then tested multiple training algorithms. Standard methods like resilient backpropagation failed on this dataset. However, the Levenberg-Marquardt algorithm, which excels at navigating complex loss landscapes to find the global minimum, processed the arrays seamlessly. Looking at the test set outputs, we see clear separation. The Levenberg-Marquardt algorithm successfully classified the medical waste subclasses with approximately 83% accuracy. A lightweight feed-forward neural network using one-dimensional features proves this strict taxonomy is computable. It provides the foundational layer needed to build autonomous sorting systems. The Varadarajan model serves as a critical proof of concept. The next engineering challenge is scaling this logic outward into the physical infrastructure of modern hospitals. The first requirement is an architectural upgrade. Because waste in the real world piles up and overlaps, the lightweight network must be swapped for convolutional neural networks, or vision transformers, capable of untangling heavily occluded objects. Second, the inference model must transition directly onto edge devices inside intelligent smart bins. Processing must happen locally, right at the point of disposal. Moving the computation to the edge while increasing the network step allows the system to handle the massive, chaotic volume of a working hospital without lagging. Once the physical sorting is automated, the data generated by those local smart bins must be routed to a decentralized cloud ledger. This ensures a verifiable regulatory chain of custody for every piece of hazardous material. That audited stream of data is then piped directly into automated ESG reporting dashboards, giving hospital administrators a real-time view of their compliance and environmental metrics. By integrating precise machine vision, edge computing, and cloud tracking, this tech stack turns a massive regulatory liability into a tightly measured operational asset. But none of this infrastructure can function without the foundational algorithmic logic that actually makes sense of the chaos inside the bin. If you're an engineer building the next layer of the hospital IoT ecosystem, review the centroidal extraction methods outlined in this research to understand how dimensional reduction drives rapid classification. The full framework for the Auditum pipeline is available in the Sireneri Journal of Science and Technology. Access the text and start building.